introduced energy diagrams. Now we're going to, and we actually talked about what they mean and such. Now we're going to take a couple minutes and talk about reading energy diagrams. So, with respect to this energy diagram below, let's look at this and let's pick it apart. So what we have is two reactions here, A and B. Either go to, we have A and B in the beginning, and they either go to C and D or to E and F. Okay? So can you see that can you see, here's my E, here's my C and D. Delta G, that we get more energy, more free energy out of it if we go to C and D. So C and D are thermodynamically favored, right? Because E and F only fall that far, right? That's delta G for E and F. So can you see that the production of C and D is thermodynamically favored because we go down further, right? These are more stable. They're lower in energy, they're more stable. So, but can you also see that the activation energy, this blue hump, is lower, right? So the number of molecules that have enough energy to get over this system here, number of particles that have enough energy to get over it, that activation energy, is greater because it's lower activation energy. So they're also kinetically favored, right? So the C and D both form faster and they're more stable. And that's what this figure means, okay? But let's consider another scenario. Let's consider a scenario in which C and D, the fall to C and D is further, so delta G, right? Then the fall to, can you see what I'm doing here? Delta G. So it looks like thermodynamically C and D are favored. Thermodynamically C and D are favored. But kinetically, right? Look at the red curve now has a lower hump here, right? So it looks like this is going to be faster. The faster reaction is going to be E and F, but the more stable reaction, the more stable products is going to be C and D, right? So again, we've got these two features of a curve. We've got the delta G, which is here. How do you spell G? And the activation energy, which is here, right? And the lower the activation energy, the faster kinetics, right? And the bigger the difference in free energy, the more stable thermodynamics, all right? So let's now also consider, sometimes we have a more complicated energy diagram. Sometimes we have transition states where, using A and B, and maybe this is a transition state because that's where we're getting the reaction to happen, okay? And this is where we have actually some reaction that actually happened. So we might get C and D here, right? And then C and D react to get another transition state where they might make, say, E and F, okay? And these are intermediates because there's a well, or an energy well, in between these two transition states, and these might go to G plus H, okay? So just making up numbers there, but to help you appreciate, transition states are at the saddle points or at the peaks, and these troughs here, or these wells, are intermediates. Transition states and intermediates. Okay. So now let's also appreciate this, that a transition state is, of course, when the two molecules or two particles are reacting with each other, and so the transition state has some feature that looks like this and some feature that looks like this, right? So here it looks like we've got chloride, right? Chloride is coming in. There's going to be a lone pair of electrons on here. We're going to do this next chapter. These electrons are going to come there, and while they do, bromide, and you can see bromide's breaking off, right? Bromide begins to break off, right? So watch this. Here's the chlorine beginning its bond to carbon, and here's the bromine breaking its bond to carbon. And the transition state is when both of those bonds are partially formed or broken. All right? Transition states cannot be observed because they are fleeting. All right? So we never see that. we see results of it, and we see sort of we can measure the energies of it, but we can't see it because it's so fleeting. All right. Now, an intermediate is a species, as we said in a previous slide, where you actually have something that is metastable. It's relatively stable. And so obviously it's not as stable as the products because it's higher, right? It's not as stable as the reactants because it's higher, okay? But it's where it's got some energy well or energy minimum. And intermediates, they are observable. You can actually see evidence of intermediates because they are stable enough to have some non-negligible existence in time. All right. Now, I'd like to point out that the transition state is going to look more. The transition state is going to look more like the product or reactant that is closer to it. So can you see that you can't tell by this picture here. This picture should be probably slightly different. Can you see that that this transition state here, the energy is closer to this energy, right? That's closer than the energy to the chloromethane, right? So chloromethane. So it's closer to this one. So consequently, this bond is actually going to be shorter. The bromine bond is going to be shorter because it looks more like the one that it's closer to, okay? Now, as we get closer to the chloromethane, as we get closer to the product, can you see that the bromine bond is going to be getting longer and the chlorine-carbon bond is going to be getting shorter, where it's more like the actually equilibrium carbon-chlorine bond length, okay? Depending on this assumption, we can generalize the structure of a transition state. We can generalize the structure of a transition state depending on whether the reaction is exothermic or endothermic. That is, which one it's closer to. We can get some general feel for what the transition state looks like, okay? And we can say that pretty nicely. So an exothermic reaction, the transition state resembles more of the reactants because in an exothermic reaction, the products are lower, right? So for exothermic reaction, the transition state looks more like the reactants. In an endothermic reaction, the transition state looks more like the products. All right, so that's a very fast, very brief introduction to energy diagrams. We're going to get a lot of value out of them. I want to spend a couple minutes on that. All right, good luck.